Hello everybody. Welcome to the first session of our three-part Applied Remote Sensing Training, SAR for detecting and monitoring floods, sea ice, and subsidence from groundwater extraction. My name is Erika Podest, and I'm a research scientist at NASA's Jet Propulsion Laboratory, as well as an instructor with the ARSET program. I will be hosting today's training and this entire webinar series. We have guest lecturers that will be presenting each session. And today I will be joined by Dr. Malin Johansson from the Arctic University of Norway. She will be focusing on detecting and monitoring sea ice with SAR. Before we begin our training, I just want to give you a brief introduction to the ARSET program. NASA's Applied Remote Sensing Training, or ARSET program, is part of the NASA Earth Science Applied Science Capacity Building Program. We provide cost-free trainings on the basics of satellite observations, data processing, analysis methods, and ready-to-use web tools in 6 thematic areas shown here: disasters, agriculture, ecological conservation, water resources, climate and resilience, and health and air quality. Our trainings are offered both online and in person, but the majority of our trainings are online. All of our training materials, recordings, and Q&A transcripts are available on our website, so you can register and participate live as you're doing today, or you can review our past trainings in your own time. We also offer a self-paced training on the fundamentals of remote sensing. Our trainings are offered at no cost and usually include a bilingual option, whether that's translated materials or the training itself is delivered in Spanish. And all trainings include only publicly available open source software and data. Our trainings are offered at a variety of levels, from introductory to advanced, to allow you to learn remote sensing based on your level of experience and need. If you'd like to know more, please visit our website. From there, you can find information about and register for upcoming trainings, view recordings, and review material from past trainings. You can also sign up for our listserv to be notified about upcoming training opportunities. To begin, I'll provide an overview of our training before we begin this session. So sea ice, floods, and groundwater extraction can be seen from space. And the objective of this training is for participants to learn how to use SAR data to detect and address these potential disasters related to these sorts of events. And they can all of these events can have a large impact not only on human lives, but on infrastructure and the economy. So SAR can be critical in informing on the ground efforts, on disaster mitigation efforts and resilience. By the end of this webinar, participants will be able to generate subsidence maps due to groundwater extraction in order to inform risk and resource management, detect and monitor sea ice to identify potential risks to shipping and coastal erosion, and detect and monitor floods in order to more closely monitor the increase or decrease of floodwaters and better inform disaster response and management. And here's the list of prerequisites for this training, starting with the fundamentals of remote sensing, followed by an introduction to SAR, specifically the first and fourth sessions of that webinar series, and then radar remote sensing for land, water, and disaster applications, specifically the second session of that series. Here we can see an outline of the training. It will take place over 2 weeks and consist of 3 parts or 3 sessions. Each session will be 2 hours long, including a Q&A. Note that So today is the first session. The second session is next Tuesday, October 31st, and the third session is on Wednesday, November 1st. Please make a note of that. All presentation slides, recordings, and Q&A transcripts will be available on the training page. There will be one homework assignment which will open on the date of the final session, which is on Wednesday, November 1st. It will remain open until November 17. A certificate of completion will be awarded to those who attend all live sessions and complete the homework assignment before the due date. Just wanted to remind everyone that if you have a question, please type it into the question box. We will be collecting these questions and answering them at the end of today's training. We will also be compiling these questions and answers into a Q&A document, which will be posted on the training website in about a week. Any questions we do not get a chance to answer live will still be recorded along with our answers. And now I would like to welcome Dr. Malin Johansson from the Arctic University of Norway. It's a great pleasure to have her here again. She was guest lecturer for the previous ARSET SAR training, where she talked about the use of SAR to detect oil spills. So very pleased that she is with us again to share her vast experience and knowledge, and this time for detecting and monitoring sea ice with SAR. Thank you, Dr. Johansson. The floor is yours.
Well, thank you. So my name is Malin Johansson, and I'm here today to talk with you about detection and monitoring of sea ice using SAR images. So here you can see a lovely image in the background of sea ice of various different age and types. And at the end of this lecture, you will know a lot more about what you're looking at right now. So at the end of this session, you should be able to understand the mechanisms behind why we can monitor sea ice, what challenges this monitoring is giving us, and how we can derive sea ice characteristics using single and dual polarization SAR images, and also how satellites and SAR in particular fit into the larger scale pictures when it comes to safe shipping and climate models. So let's start from the scratch. What is sea ice? Sea ice is ice that forms from the freezing of ocean water, and that means that this ice is very salty. It's ice that we have year-round in the Arctic Ocean. It surrounds the Antarctic Peninsula, and it also occurs in subpolar seas, such as those areas indicated here with the red arrows, the Baltic Sea and the Sea of Okhotsk. So what does it look like? Well, you saw first a SAR image. Here's what it looks like in reality when we're out there. They have many different shapes, forms, and thicknesses. So one of the earliest stages we have is the Nilas, which you see here on the top left. This forms under calm ocean conditions. And then you also have pancake ice. These are both new ice types. They're reasonably recently formed, but under very different conditions. The Nilas under calm conditions and the pancake ice under more rough conditions. We also have leads here, so you can see a lead that's open up in the thin ice areas where you can see the open water in between. But most people maybe think more of the thicker ice types, the ones we see polar bears standing on. And these are the first-year ice and multi-year ice types. Over here, there's 3 different pictures of thin first-year ice, rough first-year ice, and also multi-year ice. And here is the sort of basic mechanisms and classes of ice formation. We have the new ice, which is the first ice that forms. It has a high salinity, but it's not very thick. We then go through the stages of young ice towards first-year ice and finally old ice. The old ice, there we're talking about ice that is more than 2 meters thick and has survived at least 1 melt season. And this is also the least salty of the ice types that we have. So what does it look like? We often take cores from the sea ice. So we drill ourselves with a looks like a straw through the ice to take samples from it. And you can see such an example on the left here. And you can also, if you look at from the edge here, you can see that there is quite a lot of pockets or air bubbles. This is where the salt has accumulated in these so-called brine pockets. And over time, the salt drains out of the sea ice and leaves behind cavities, which are then filled with air. And as the sea ice ages, the salinity, density, and the surface roughness changes. And if you look in the diagram on the right, you can see that the top of the sea ice normally is colder. It has more of an air-like temperature, whereas the sea ice at the bottom has a temperature more similar to the open ocean underneath it. And the salinity has its lowest values at the top and the highest values at the bottom. And all of these changes affects what the radar can see. So here is a close-up we've seen from the side, sliced in a very, very thin sheet. It's the same core, but it's now cut into a small piece. And we can see that the crystal structure looks very different. At the top, we have the so-called granular ice, and lower down, you can see more columnar ice. And these vertical, or the structure of the crystals, affect what the radar can see. So now you know how the ice forms and where it's located, but it doesn't exist all the time in all areas. And that is because in the summer, it starts melting and starts disintegrating. First, the snow on top of the sea ice melts and melt ponds start forming. And you can see such a melt pond here in the ice flow. And this is at the very start of the melt season. So you have the melt ponds just sitting on top of the sea ice. And this means also that the albedo is decreasing and the heat absorption in the ocean can start increasing. And over time, these melt ponds grow in size. Some will be penetrating all the way through the sea ice, so connecting the ocean to the ocean from both above and below. And this causes further weakening of the sea ice. And due to interactions with the surrounding ocean, the ice then starts breaking into smaller fragments. But you can also have the melt ponds that just reside on top of the sea ice, but they still cause a weakening of the sea ice structure. And these are changes that we can very clearly observe with SAR images, and is something that we really need to account for when it comes to the monitoring and detection of the sea ice itself. So what does this look like? Well, you already seen some SAR images, and here is a movie of sea ice that we tracked with sea ice drifters in the spring of 2022. And at the start of this video, the sea ice is very cold. We can see a lot of structures. And about now in the images, the temperature has risen so much that the snow starts melting and there's a clear change in the SAR signatures. We have simply gone from the spring and winter into the summer season, and now the ice really starts breaking up and turn into very small pieces. So if we just sort of stop the movie and look at two sets of images, we have the freezing conditions on the left and we have the melting conditions on the right. And the first ones here are from the end of April and early May and in 2022. And the last two images are from the end of May and early June 2022. And things look quite different in these images. And this is simply caused by the melting. These images were taken at the same time as we had a campaign where we collected in situ data in this region. So we happen to know that in the images on the right, the temperature has turned positive and we really started having melting. The melting itself started around 27th, 28th of May, and this first image here is from the 31st of May. So when we monitor, we really need to account for these kind of changes because the ice itself has not necessarily changed much here, but what we can observe in the SAR images has changed quite significantly. And how we deal with these kind of changes is something you learn more about in the next hour or so. So you probably all heard that we have the Arctic sea ice, and the Antarctic sea ice also is changing. And you probably then heard that it is disappearing. So what do we mean with the ice disappearing? Well, we can first here look at the ice thickness. So here on the left is an image from 1985. This is what the conditions were like in March then. And on the right is an image from March in 2022. And the older ice here has been marked with in red, followed then by yellow, green, and the youngest ice is the blue. And you can see that there's a lot less red to the right and more blue. And the red indicates then the ice that is more than 4 years old. But you can also here see that the ice is not equally distributed across the Arctic. The Canadian archipelago, that's where we have the oldest sea ice, and also around when you go towards the Alaskan side. And if you go towards the east, here's where we have the youngest sea ice. So the changes across the ocean varies. And today, a larger fraction of the Arctic sea ice is less than 1 year old than it used to be. And yeah, you have the oldest and thickest ice in the west and the youngest and thinnest ice in the east. So I talk about here as the age of the sea ice. How do we actually determine the age of the sea ice? Well, this is not something that we do with SAR images, but we start counting from the 1st of September or the start of the freeze-up season. And once the ice has survived one melting season, when we have these melt ponds, then we say that the ice has turned to 1 year old. And this roughly happens then on the 1st of September. So what do we actually monitor? So this lecture is supposed to be about monitoring and detection of sea ice. Well, we use different parameters. We often talk about 3 different things. First one is the sea ice extent. And here you can see an image from quite recently, the 27th of September in 2023. And this is around the time when we say that the sea ice is at its lowest, the sea ice minimum. We also talk about the sea ice concentration and the sea ice type. And on the right here, you can see a sea ice concentration map. We talk about the different types, and I already hinted towards that we have the newer ice and we have the older ice. So that's one thing that we also try and monitor from space. And we also talk about the finally is the stage of development. Now, how we monitor sea ice was not necessarily designed with a radar in mind. A lot of the terminology that we're using, such as the WMO nomenclature, was devised while people were standing on the ice and were looking at the ice itself and imagining what it meant to them in a way. And SAR does not see thickness, or to a large degree cannot see thickness. And when we talk about the ice stage of development, we start with the open water and then new ice, nylus with frost flowers, and so on as the ice thickens. But SAR, on the other hand, sees roughness, surface roughness. So we're talking about millimeter to decimeter range. It sees volume in homogeneities, such as air inclusions, these brine pockets that you saw pictures of earlier, the snow grain size, and so on. So when we talk about SAR images, this is what we can see, and we somehow or the other needs to relate that back to these ice type that WMO has established. So yes, the ice vary over the year. We have the seasonal cycle. The ice is lying on top of the ocean. This means that it's drifting. It is not stationary. We have 2 areas in the Arctic when the ice is disappearing through. We have the Bering Strait. You can see as a top red triangle or rectangle here. And then we have the Fram Strait, which is the lower rectangle between Greenland and Svalbard. In the Fram Strait, we have the fastest flowing sea ice in the world, or in the Arctic Ocean. And this is an area that is very challenging then when it comes to sea ice monitoring and detection, because the 2 SAR images will see very different things, even if they're looking at the same location, but at different points in time. So that's one of the reasons how the sea ice extent can vary. It can melt, but it can also drift away. So why do we monitor it? One of the first things is that it controls the albedo in the Arctic Ocean. When there's no sea ice, The solar energy is absorbed by the ocean, and if we start adding sea ice, the albedo changes. We have a higher albedo, and the sea ice reflects then more incoming solar radiation, and the ocean temperature can increase less. If we on top of that add snow on the sea ice, the albedo gets even higher, and most of the solar radiation is simply reflected away from the ocean. So this is why we are using this also then for climate modeling. But the ice is also something that we're having to deal with if we're having ships or if we're living in the Arctic. The sea ice is a hinder when we are trying to move our ships. And we then need to use SAR images or other satellite images to help our ship routing. Because you can see here, the image on the left, we see an icebreaker, and it's actually surrounded by quite thin ice. But if you're looking at the icebreaker on the right, there is quite a lot of deformation there. And these two areas is quite different how challenging it is to move through. And generally, all ships will try and avoid areas with heavily deformed or very thick sea ice. So for the operational sea ice mapping here, we're looking for optimizing the icebreaker routes or routes for any ship for that matter. We try and go towards the areas that are indicated with green arrows here, which are leads, and we try and avoid the areas that are indicated by red arrows. So the leads are openings, and obviously the ridges are closings where sea ice has drifted towards one another and caused obstacles for us. And yeah, the sea ice moves. So here we can see evolution of SAR images where we simply have divergence and convergence areas where one area may have been very easy to travel through at one point in time, but over time it starts having a convergence and the area becomes impassable for many of the ships. It is also used, the sea ice is also used as roads or simply part of the general infrastructure. And there, they want to know where there's ridges and deformed sea ice areas because they're very challenging to move through, and you would look for something that's flatter, which is much easier to traverse. We also want to know where the sea ice is to monitor the coastal erosion. The sea ice would generally act as a barrier between the coast and the open water. And you can here see sea ice extending out from the coastline in some area of Svalbard. And for each day the sea ice sits there, it actually protects the coastline from further erosion. So if we can include the presence of sea ice into coastal erosion models, we can actually get a much better estimate of how the coastal erosion is affecting these areas. And last but not least, the importance for the climate system. Leads will enable heat and gas exchanges, something the sea ice itself will limit. The frequency and the size of the leads and polynyas are therefore essential to have a good grasp of when we calculate the regional heat fluxes and budgets. So you can see here, heat flux from the sea surface is between 100 and 1000 watts per square meter, whereas if you have 1 meter thick sea ice, it gets reduced to between 5 and 20. So it's a very important parameter to account for when we're doing heat and gas exchange estimates. So how do we do it? How do we get from these kind of low altitude images taken from a plane to monitor sea ice? Well, we use SAR images for this. And we derive sea ice maps. So how do we actually derive the maps? Well, they are drawn by hand. We use expert knowledge and we use history of sequence from SAR images. We often look at yesterday's image from the past or the last hour in this day. We use information provided from ships. We use other satellite sensors, such as passive microwave sensors, and we also use weather forecasts to indicate how the ice is likely to have moved from one day to the next. But obviously, we have a lot of satellite images being taken every day over the ocean, and we are simply no longer able to keep up using all of these images as input into our sea ice maps. So there's a lot of work ongoing right now to use AI or machine learning techniques to improve the ice charts. Though as of yet, this is still under investigation. And one of the reasons for that is very important to avoid misclassifications regarding hazardous ice conditions. You do not want to send a ship into an area which can be very challenging or even dangerous for them to be in. So yeah, I hope you all know that, well, SAR images, they can penetrate clouds, therefore they can work during the polar night. Something that's very essential when we're going to work with sea ice detection. So because a few months of the year, there is no daylight in these regions. The weather can be cloudy. We have between 70 and 80% cloud cover at any point in time. And in summer, you can also add the additional fog. The SAR images are therefore essential if you want to have high resolution, cover large areas, and at the same time have year-round coverage. But the SAR is not easy to intuitively interpret. And we need to understand how the radar signal interacts with the ground. So here you can see on the right, we have some SAR images, and on the left, we have some optical Sentinel-2 images. For the SAR image, we use the force color composite. And you can see that it's very easy, though, to separate the sea ice and the water in the optical image. But in the SAR image, it's not that easy, though other things are starting to become apparent, such as the ridges. And let's look at some more examples here. I hope you can see the flicks between a Sentinel-1 and a Sentinel-2 image. So you can see here that the SAR image doesn't tell the full story, but neither does the optical one, because in the optical one, we can't really see through the snow. And there are areas where we have more ice and less ice, and it's simply obscured by the presence of snow. And here's another image. You see this slight shift in time, so they're not taken at exactly the same time, but you can see a lot more information about where we have deformation in the SAR images than we can in the optical images. So the positive side is using SAR images as it works at night. It can see through the clouds and it can see roughness, which meant that we can use this to detect deformed sea ice areas. And that is something that is very useful for safe shipping. We have some challenges. The radar intensity signatures are ambiguous. It's not easy to directly connect the sea ice properties, and there's multiple scattering scales involved. One of the problems we have is, for example, the young ice types. Young ice can be bright due to the presence of frost flowers. These are ice crystal structures that appear on top of the sea ice. And in the radar, these two images that we can see here would look very similar. This is simply because we have volume scattering from the frost flowers in the image on the lower right, and we have a volume scattering from all of the deformation and all these ridges and areas that you can see in the upper image. Young ice has a very large range of SAR signatures. You can see here 3 pictures of younger ice types, and they are all very, very different in the SAR image, though they are perfectly safe for any ship to go through. They have a high salinity, but different deformations and different presence of frost flowers and other things. And if we look here in the SAR signature, so this is the VV channel, and the blue crosses here indicate new ice. And hopefully you can see here that they actually cover more or less the entire spectrum, entire range here for all the different frequencies. We have an X-band, C-band, and an L-band image. And simply the newly formed sea ice it covers it all. And this is something that we need to account for when we're going to do automatic monitoring of sea ice. The melt season. I already shown you some images. The melt season changes everything. The separation between wet sea ice, melt ponds on the sea ice, and open ocean is very challenging. We're trying to separate also between the open ocean and the sea ice. The open ocean, we can have the wind affecting the areas there. So the backscatter values are wind speed dependent. We also have the propagation and scattering of radar waves in snow and ice layers that cause complex interaction processes. It is therefore challenging to come up with one solution that will work year-round, be it an AI, machine learning based, or a manual classification based type. But let's start looking now a bit more on the SAR images themselves. What type of SAR images do we use operationally? We rely primarily on scanned SAR images because they have a good coverage. These days we use data with the HH and HV channels. They are provided by the RadarSat Constellation mission. They're provided by the Sentinel-1 data, freely available. Any one of you can start your own CIS classification or CIS monitoring. We have good backscatter signatures, and over time we have learned how the CIS interacts with the SAR over these CIS areas and CIS types. You can already here see an advantage of having two channels. So at the top we have an HH channel, at the bottom we have the HV channel. The CIS edge is somewhat challenging to see in the HH image, but if we look in the HV, we can clearly see the edge between the open water and the CIS. This image here is also taken from the Baltic Sea in an area between Sweden and Finland, and we only here have seasonal ice, so the ice is reasonably easy to detect because we don't have the challenges with the multi-year ice. And here it's an oldie but goodie. It's an ERS-1 SAR image from 1992. Unfortunately, or fortunately, the ice has not really changed since then. If we look in the red rectangles here, we can see two different types of level or smooth ice. And if we look in the orange box, we can see more ridges. And these are the kind of things that we are then using this knowledge on how the different ice types look in SAR images when we want to derive monitoring and detection of sea ice. And over time, we've also learned how the backscatter signatures change. So on the left here, you can see a little bit of a reminder on the ice growth process from the fragile ice or from the calm ocean until we get to ice sheets and thicker ice. But on the right, you can also see the radar scattering coefficient and how it changes over time as the sea ice thickens and the salinity changes. So we start with having reasonably low backscatter values. They drop once the ice starts forming. Then the values increase again, only to drop down again. So there is these kind of changes with ice thickness we need to account for, and we can have all of these different ice types at any given point in time in your SAR image. So there is a lot of factors we need to look into both from how the sea ice affects the SAR image and then how the sensor parameters affect how we can study the sea ice. But let's take it one thing at a time. Let's start first with the sea ice properties. The difference in salinity will affect the dielectric constant and the penetration depth. So yeah, the sea ice is salty, it's made out of salt water. It accumulates in these brine pockets and channels. And once the ice has started to form, the brine starts being expelled from the sea ice. So you have sort of the saline ice you can see in the image here on the left, which has a higher salinity, and then lower down, the salinity actually decreases. There can also be a salty layer at the surface that affects the radar signature due to changes in the dielectric constant. If the brine layer is at the bottom, it leaves behind empty pores, enabling volume scattering. And on the right, you can also see a first-year ice picture where you see these brine cells. So yes, which brings us to the porosities and inclusions. So yeah, there's another illustration with one more undulating surface where the snow grains in the snow layer and brine inclusion of the sea ice here. So we have the brine inclusions and then we have the seawater underneath, and depending on the size of the snow crystals, that will also affect the radar backscatter signatures. The photo here, the snow grains, there is up to 2 millimeter in 2 millimeter lens, and they're approximately 1.2 centimeters big. So they will affect the sea ice scattering. We also have the surface roughness and topography. So a bit higher up in the, we've looked in the ice itself, but now we can look at the surface of the ice. And here are some pictures. We can see we have rough ice at the top of the leftmost pictures, and then we have thinner new ice at the lower left. If we look in the SAR image to the right, there's one channel, the HH, from a fully polarimetric RADARSAT-2 images. It contains a few sea ice types. Within the white rectangle here, we have young ice. This ice here was observed during the Mosaic expedition. If you're interested to learn more about the Mosaic expedition, I urge you to just look online. There's a lot of useful information out there. So the ice here we know is rather smooth and is slightly less than 30 centimeters thick at this point in time when this image was taken. We have the bright area within the blue circle. This is a ridged area. We have a lot of deformation in this area. And then the very dark area within the purple circle is refrozen melt ponds. And the surface here is very smooth. And finally, then we also have the layers. We have the snow ice interface, we have the sea ice water interface, and we have the snow cover with different densities, grain size, and moisture levels. So you can see here also an illustration at the bottom where you talk about the different scattering properties when we have multi-year ice, first-year ice, and open water. We normally talk about the snow layers as dry snow layers, and then the radar can see through them. If we here compare an optical image at the top and an L-band SAR image at the bottom, the snow is largely impenetrable by the optical sensor, but we can clearly see through it with the radar. Though we can see some ridges in the optical image because there's shadows and these kind of features that we are used to looking at, but the ridges are very easy to see in the SAR image. And once the sea ice is thick enough, the return signal will come from the snow on the sea ice and not from the sea ice and water interface, because you can also see some open water areas where you see some structure in the SAR image as well. Radar operated between L and X band looks through the dry snow, and this is an advantage for many of our applications. But we also have other KU bands where it may not do, and we are using that for when we want to derive the ice thickness and so on. But that's for another lecture. But the snow is not always dry. So here are some pictures taken from a recent campaign, an AutoMelt campaign, which was targeting the melting conditions in the Arctic Ocean. So it was planned to be then between May and June in 2022. A lot of snow pits being done, and here are some of those images. At the start of the cruise, we had very dry snow. You can see, you can almost feel how crisp the air is in this image. On the other hand, if you look towards June, the onset of melt had started, and the melting had started in the snowpack itself. And you can probably see at the bottom there that the ruler here sits in a bit of slushy water. And here we simply see the effect of the melting, as I showed earlier in the lecture here. Between the freezing conditions and the melting conditions, we start seeing the water rather than the snow or the ice underneath. And on the right, you can also see two images very close in time, but here the indication or the radar signature changes and indicated the surface has gotten wet. So all of these things we need to consider and how the sea ice affects the SAR imaging. But of course, we have the SAR sensor itself, where we have different polarizations. So I already talked about the fact that we use HH and HV channels. And you can see here, the HV channel is really useful to separate open water from sea ice. And this helps us reduce the ambiguities when we interpret the radar signatures in terms of the ice types. The water appears dark and is better separation between the multi-year ice and the first-year ice, or the level and deformed ice. And the sensitivity to the incidence angle is less. And I will come back to the incidence angle in quite some detail very soon. So what we can see here, we tracked here the same sea ice over time. This is the same image, it's the same movie that I showed earlier. And through the use of drifters, we could ensure that we followed exactly the same sea ice flow over a time period of about 2 months. Or here, actually, it's just a little bit more than 1 month. This is a multi-year ice flow, and we're using Sentinel-1 images. And to the left here, you can see we have freezing conditions, and to the right, we have melting conditions. And the blue dots are indicative of the HV backscatter values, and the orange one of the HH. So you can see in the freezing conditions, things are pretty stable. We don't have that many changes, but we start seeing an obvious change when we go to the melt season. And we, in this campaign here that we put out drifters, we didn't just put out one drifter, but we put out many drifters, and we put them on different ice types. And here we can see multi-year ice, so ice that has survived many melting seasons, and then first-year ice that has survived only one. And you can see that the changes in backscatter varies between these two different ice types. Where for the multi-year ice, the backscatter values gets reduced when the melt season starts, and for the first-year ice, actually the backscatter values increase. And using these kind of changes in backscatter behavior, we can determine which ice types we're looking at, provided that we follow the same ice over time. But this also then causes obviously challenges for the development of automatic sea ice classifications, because the ice is not looking the same year round. And yeah, I already talked about the incidence angle. The incidence angle is a little bit of a nemesis here, because we know the fact that the radar backscatter is reduced with increased incidence angle. This is something new, we've known for a long time. And smooth targets, such as the ones that are here, have a sharp drop in the radar return with increased incidence angle. So we need to account for this in any monitoring of the sea ice. So we can correct it using one slope across the entire image. That's one way of doing it, but the ice types do not have the same changes across all the incidence angles. So it's not perfect, but it's a very good way of doing an automatic correction. We could also look at for one correction for each different ice type. But firstly, you can see on the right here, we have some gray level concurrence parameters with HH contrast, HH energy, and you can see that the return values here change quite a lot with change in incidence angle. But the changes across the scene is dependent on the material, and here you can see an image showing open water and multi-year ice, and doing one correction for both of these two is good, but it may not tell the entire story. And also you can see here the separation between the two different materia is easiest in this example at an incidence angle range, sort of, or most challenging, between 30 and 35, which is in the center part of the Sentinel-1 images, for example. So we really need to get a handle on the incidence angle effects. And here I can just show another example. So the sensitivity is stronger for the smoother surfaces, so the thin ice and the calm open water, than for the rougher and deformed or wind roughened water areas. And here you can see the same flows are indicated within these two red circles, but with slightly different incidence angles. So to the left, we have very high incidence angles, 42 to 45, and to the left, we have very low, between 19 and 22. So you can see that these values change quite a lot, and any automatic classification needs to account for this and realize that it's the same ice type. We can address this once we know which sea ice type, such as was done here. If you look on the left, the incidence angle has not been accounted for. And if you look on the right, it has been accounted for. So you can see the importance of adjusting for the incidence angle, both over time, but also between different images, so that we can see that the changes we're observing is actually a physical change and not a change of the sensor itself. So let's also talk a bit about the resolution and the sensor noise. We have talked about the incidence angle, we have talked about the polarization. Here on the left, we can see an airborne SAR images over sea ice, a pixel size of 5 meters. And on the right, a satellite SAR image with a pixel size of 12.5 meters. They're taken over the same area at the same time. And as you can see, there are quite a lot of things that you can still identify. Some of the ridges are easy to see, and some of the open water areas or thinner ice areas we can observe. But of course, these airborne missions with a very high resolution, they cover a much smaller area. So when we want to do operational ice monitoring, we need to have a balance between coverage and resolution. And here we can also see an image from the Fram Strait. Remember, this is the fastest flowing sea ice drift, and we need to have them very close in time. Here is a time difference of about 1 hour, which means that things have moved and they're not lying exactly how they were before. But at the top here, we have 150 meter resolution. And at the lower one, we have a 2 meter resolution. So things are quite different. But we can still observe quite a lot of the flows clearly. And the more deformed sea ice flows have clearly high backscatter signature in both images. And the level smoother thinner ice is clearly recognizable as the darker areas. And we have used information from such campaigns to help us interpret more what we can see in the satellite SAR images. And frequency, let's talk about this. It's one of the things that I'm very passionate about. And we also have a lot of new and exciting upcoming missions, such as the NISAR, ALOS-4, and ROSE-L. And we already have existing L-band missions, such as ALOS-2 and SAOCOM. And it's something that is becoming more important to consider because the melt season is lengthening. We have a longer melt season in both the Antarctic and the Arctic. And we know that the L-band SAR enables easy detection of sea ice ridges, and it can account or manage a little bit further into the melt season before it gets very affected by the wetness levels. So why the different frequencies? Well, they have different penetration depth. With X-band, we have approximately 3 centimeter wavelength and a very small penetration depth. With L-band, we have a 23 centimeter wavelength and a much greater penetration depth. Here are 2 images taken at the same time. I'm hoping everyone is familiar with Pauli images, because that's what I'm showing here. And on the left, we have a fully polarimetric C-band image from RADARSAT-2, and on the right, a fully polarimetric image from ALOS-2. The images were taken in early May of 2015, and you can clearly see the deformed major deformation zones in both images, circled here in the sort of yellowy green color. But there are some differences in the thinner ice areas that is caused by a difference in wavelength. And yeah, sea ice, as we've seen, is a difficult medium, or we have the snow on top and the snow ice interface, and then the ice water interface. And depending on the wavelength, the penetration would reach different depth. The X and C band generally scatter from the surface, and the S band can penetrate partially from the surface into the ice volume, and the L band scatter is generally from the ice volume itself. So because we're looking at different scattering mechanisms here, because of different penetration depth, this can give us added information for sea ice classification. So the penetration depth of different sea ice types can be seen in the image here. I've tried to indicate with green lines where you have roughly C band and L band in this graph. And for the L band, we have a higher penetration depth, up to 1 meter. For the C band, we have in the range of 0.5 meter, and for the X band, a maximum of 10 centimeters. And changes in salinity also affects the electric constant, as you can see here. So what this means is that the X-band shows the largest contrast between first-year ice and multi-year ice. X-band is also more sensitive to the snow on the sea ice, and specifically we start having layers in the snow top layer. Such layers can be wind-hardened layers, rain on snow events with subsequent freezing, warming events, and also ice lenses. And changes due to the snowpack means that the X-band is more sensitive to the onset of melt than C and L bands are. And we will particularly exploit the lower sensitivity to onset of melt in L-band images. So just to show some more examples here, we have a C-band image on the left and an L-band image on the right, and you can see that they do provide complementary information to one another. Though the incidence angle for those who've already spotted it is slightly different, so it's not an entirely fair comparison here. But again, remember the ice drift in the Fram Strait is fast, and here we have a short time separation. But you can see that the open water areas, the thin ice areas, appear very dark in the L-band image and has a lot more texture to it in the C-band image. So in A here we have zones of new ice information, much larger signature variation in the C-band. We have some B, value B here at the top that indicates older ice flows, and you can clearly see this in the C-band images. And then the number C here is brash ice and moderately sized flows of level ice. And you can see here the intensity contrast is quite large in the L-band image. And then in D, we also have some shear zones, deformation zones, which is easy to observe in the L-band images. So what do we do? Well, there is a lot of work ongoing now to combine the two frequencies. L-band and C-band has been shown now a number of times to improve the classification accuracy. And first here at the top here, you can see an C-band and an L-band image. They have been drift corrected, so they're completely aligned with one another. And we first have results if we train a CS classifier using just the C-band data. And here, if we use the L-band data, and here finally, if we combine the C and L-band data. And hopefully you can see here that the young ice areas indicated in purple, we can, by combining the two frequencies, we can much better identify these areas. They're particularly shown here in the blue and the yellow triangles. We can see much better results by combining C and L. The formed areas in the red rectangle, we can also see quite well that the combination of the two is superior. And if we can look here at another example, so different images, but we can see that the L-band is generally much better at detecting the deformed ice areas, or the combination of the two. And at no point in time is the L-band completely superior. The combination of the two of them is equally good or better. And if we're looking at only the combination of C and L-band can fully capture the young ice in the open water within lead systems correctly. So yeah, how do we do this? Well, we go from the images or the information we've learned about how the SAR interacts with the sea ice that we can observe from planes or from in situ campaigns. We account for the snow, and we use this information that we've learned and take that towards the SAR images, where we can then identify ridges, young ice, and refrozen melt ponds. And over time, we take a whole range of all the available SAR images within reason, and we use them to produce these sea ice maps. And reason for wanting to do so is that we now have SAR systems have been up and running for such a long time now that we can derive a long time series of the sea ice extent and the cover in specific areas, such as shown here. This is from Kungsfjorden or Svalbard, but now the records goes back to the early 1990s, and we can actually see how the season length has shortened or increased, and how the ice, when it forms, how stable it is. And we use this to monitor and detect global changes. so such as looking at the Arctic sea ice yearly minimum. So from the lecture today, I hope you now learned that we can observe surface roughness with SAR images, and the sea ice takes many forms, so we need to account for the different roughness scales and how they relate to the sea ice itself. We need to look at sensor specifics such as the incidence angle and frequency and how they affect the detection and monitoring capabilities. The great news is the SAR can be used to detect and monitor sea ice. When we can have more than one channel, that is great because, for example, the HV channel provides better separation between open water and sea ice. We can, for most part, not derive ice thickness using SAR, which makes using the WMO classes challenging, but we can identify areas with different deformation. The young and thin ice is the most challenging ice type. They can look both like smooth open water and heavily deformed multi-year ice in the SAR images. But we have learned how to account for this over time, and we can now also use long time series in climate models. So now that you have seen how the different sea ice types can affect the radar backscatter, you're now ready to perform your own sea ice classification. Ideally, we would like to use overlapping SAR and optical images, and many images at that. But today we'll work on one image. So pick one that contains both fast ice as well as drifting sea ice. And you can see the name here, and it should also be made available to you. The area is in the Belgica Bank area, and an area where we have a lot of Sentinel-1 images available, as well as from the Extreme Earth project. There's a data set that you can use for training your own sea ice classification. This also happened to be an area we visited during a cruise in April-May 2022, where we did perform sea ice classification validation. So we know quite a lot of the different ice types that we're going to be looking at today. So how to go about it? You need to first open the file in SNAP, and we're going to do the standard pre-processing steps, doing the calibration, the thermal noise removal, and there are many different ways of doing this, and you can search for Sentinel-1 thermal noise removal if you want to know more about this. You can also do a filtering step or a multi-looking step. For now, I'll stick with the 40 by 40 meter pixels that we have from the EW mode. So first, the thermal noise removal, and then the calibration of the images. And once you've done that, you should get an image that looks something like this. In order to speed up the process a bit, we're going to do a bit of a subsetting. So I have proposed here an area that you can cut out. This removes the fast ice area, which is a little bit challenging for any sea ice classification as well. So we now have an image that we can classify. And today we'll do a random forest classification. And I've decided we're going to do some training data for this. Deformed ice, level ice, young ice, and open water. And the training data is generated by identifying polygons containing the different ice types. So you need to first do a new vector data container and then start doing your areas. So here I'm going to provide a little bit of help. So I first looked into the deformed ice areas, and you can see on the left we have the HH channel, and on the right we have the HV channel. And you need to now derive a number of RUIs. And you should remember by now that the incidence angle effect is important to consider. So you shouldn't just collect RUIs within one small range, but you need to spread them out a bit. So here I identified some deformed ice areas and also some level ice areas. And furthermore, I then continued to do some young ice, pink areas here, and some open water areas. Part of the reason we know there are open water areas is also we looked at a time series of Sentinel-1 images over this area, and we can see that the ice there has moved. So we know that the area where we now have open water did not have any, or the ice moved away from there in the last day. You can then set up your random forest. So you do a classification, supervised classification, and then random forest classifier. You find the folder image with your training data, and you then select the classes that you like to include. And for the imaging classes that I selected, my results turn out like this. I also now pointed towards where we actually were with the ship within this image. An area that here has been classified as open water because it's very flat area. So the classification is not here perfect, and it's something that we need to continue working on. But for now, this is to show you how you can do your own CS classification map using a random forest classification. So I hope you enjoyed this lesson here. I'd like to acknowledge a big thank you to all the people who helped with setting up this lecture. Wolfgang Dieking, Johannes Lose, Katrin Tellman, Dennis Demchev, Truls Carlsen, and Torbjörn Eltoft. They provided both slides and input and helpful feedback. And I also like to acknowledge all of those who target order satellite data to overlap with the C2 data campaigns. Without the temporal and spatial overlaps, a lot of the work that we're doing now would not have been possible. And of course, those who participate in the fieldwork collecting the in situ data. And should you have any questions, you can contact me. Here's my contact details. And I also urge you to look at the ARSET website for other lectures and the sister programs as well. So also some resources for the latest about the Arctic and Antarctic sea ice. So today I've only talked about the Arctic sea ice. There's a lot to be said also about the Antarctic sea ice. And you can look at some extreme Earth dataset that will provide training data for your own sea ice classification. If you want to know more about the cruise that I mentioned a number of times today, you can also see our cruise report. It's a lot of good references that you can look at. And for now, thank you, and let's start with the questioning.
Thank you, Dr. Johansson, for that wonderful presentation. We've been receiving lots of questions, and we are ready to start our live Q&A. Wonderful. So we've been assembling the questions that you've been sending on a Google Doc, and we will be sharing that Google Doc here with you shortly. I'd like to note that as you've noticed, this is a new platform that we're testing, WebEx, and so for those of you that have attended ARSET trainings, it's a little different. Here we ask that people post their questions in the Q&A window. So if you go to the bottom right, there are 3 dots. And if you put your cursor over those 3 dots, you'll have a menu that opens up with 3 options: Q&A, notes, and captions. So if you select Q&A, that will open the window where you can write your questions. I noticed that some of you have also been writing questions in the chat box, so we've been collecting those as well. So Dr. Johansson is here online, and I will start reading the questions, and she will respond. All right, so the first question: what are we looking for between freezing and melting? Are we talking about change detection? Go ahead, Dr. Johansson.
Hello, I hope you can hear me well.
Yes, loud and clear. Thank you.
That's good. So I guess, well, when it comes to sea ice, it has a seasonal cycle, as I hopefully covered quite well in the lecture. And we have the freezing starting in September and then melting somewhere between April and June. This depends a little bit on where in the world you're located. Also for the Arctic here. And once the melting starts, we start first having the melting of the snowpack, and then we have the melting of the sea ice. And then we start seeing changes in the radar backscatter signatures. So if we're talking about stationary ice, we do actually use change detection methods to detect when the melting starts. So yeah, we can do change detection there. If we are in areas such as the European side of the Arctic, our ice is drifting very fast. And then we're not really talking about change detection per se, because we have between 2 images, we're simply not seeing the same ice in them. But of course, when the melting starts, we're seeing a change in the backscatter signature. So I hope that sort of answered the question.
Great, thank you. Let's move on then to question number 2. If we use L-band SAR, can we estimate the thickness of sea ice using coherence and phase values, as L-band has a higher penetration depth, or maybe a band with a even higher penetration?
Yes, we can to some degree estimate the sea ice thickness using L-band images. There is though a limit, so above 0.5 meter, we simply cannot. The signature is only from within the ice itself. We no longer have a change because we have a reflection between the ice-water interface. So up to about 0.5 meter, we can with L-band, or has been shown already 20 years ago with some Japanese colleagues, Wakabayashi. So I put a link here to a paper. I'm not sure if it's open access. But there the simplest method here is simply to use the VV and HH ratio, backscatter ratio. So that obviously, for those of you who paid attention with the SCANSA data that we have, which we have often in the HH-HV, we cannot use this ratio because we're simply lacking the VV channel. But it is possible, and the best results has been achieved with the VV-HH.
Great. Question number 3. How helpful are optical satellites in detecting sea ice? I'm assuming there will not be a great cloud problem near the poles.
Yeah, no, optical images are great. There is a lot of applications where we would love to use them, but yeah, clouds and fog. And here we're talking about the Arctic, so we have a number of months of the year where we simply don't have any daylight. So closer to the poles, it's less of a problem than in the marginal ice zone, i.e. where the sort of the ice zone ends. But it is more of a problem in the summer months because we have the temperature difference between the water and the air. So we're looking at about a cloud cover of still 70 to 80%. The optical images are useful, but once we have snow on top of the sea ice, we start not being, it's not as easy to separate the different ice types. It can be a challenge to see ridges and deformation if we don't have any shadows. But optical images are excellent for separating open water and sea ice. So they are helpful. And when we want to train machine learning methods, AI, or other things, we often look for overlaps between SAR and optical images, simply to have a better classification and more confidence in our labeling.
Okay, question number 4 starts out with a statement. Ice is not getting older. The defrosting times are shorter, which means there's less ice formation, which means there's less albedo or lower albedo, which causes more local warming, which then leads to less ice formation and even lower albedo. The question here is, has anyone tried albedo change comparison for predictive purposes?
Right, so I'm more of a SAR sea ice expert, and we cannot do albedo from SAR really. But there has been some quite recent work on albedo retrieval, where it's been used to look into such things as how the change in albedo will affect biological productivity. So I provided here some links to open access publications where they look simply, albedo retrieval, and also from a little bit of commercial for this very large drift campaign that we had in 2019 and 2020 from the Mosaic Sea Ice campaign, where they also looked at the Arctic sea ice albedo.
Okay. Question number 5. What sea ice properties are more easily classified by changing the polarization?
Right, yeah, so sea ice properties. Well, The HV channel is very useful if we're looking at ridges or like this really rough and deformed sea ice area. So we talk about ridges and rubble fields and these things. The polarization then changes with interaction with the surface, so they are very useful for these deformed ice areas. As I said before, the two co-polarization channels, they're very useful for the thinner ice areas. The ratio there is often something that we use to simply identify where the thinner ice areas are. We also use the HV channel to separate sea ice from the open water. The open water is one of the arch nemesis that we have for automatic sea ice classification, simply because the open water can have so many SAR signatures. It can have very high backscatter, it can have very low backscatter. So we often struggle to separate it from the deformed ice areas and also from the new ice areas. So the HV channel is not the ice properties itself that we're using it for, but we're using it to separate the open water from the other areas.
Okay, question number 6. What scene sizes are used or did you use for this type of application? So for example, the SAR scenes, what sizes are they? And what resolution are these images typically?
Yeah, so operationally we rely on the SAR images for any detection and monitoring of sea ice. And we do that because of the large aerial coverage. So here we're talking about swath width somewhere between, well, 300 and 500 kilometers. These days there are some even wider SARs coming up soon. But we are then having a pixel size of typically 40 to 50 meter resolution. So when you're looking at the actual resolution is about somewhere between 80 and 100 meters.
Okay, along those lines, how did you calculate the backscatter of each single point in the curve? And does the point represent the average of an area?
Yeah, so I tried to go back and see which particular slide this was, but I suspect it's the one where we had the change in backscatter values over time. So at that particular area, we placed our drifters on the sea ice, and therefore we follow the same ice flows over time. We also looked at other recently identifiable areas in the vicinity of this. So we then managed to extract a number of RUIs from each of the images. But each point there represent the average backscatter within that RUI, so normally one ice flow. And then we use that same ice flow and average the same area of the ice flow for each of the different points. So I'm pointing there towards a poster which has a little bit more details on this.
Okay, and just to clarify for those that might not be so familiar with the terminology, the ROI is a region of interest.
Yes, so an area where we basically had made a little, a line or made a circle over the specific area, and then we take all the values within that circle and make an average of that.
Excellent, thank you. The next question, number 8, what is the reason for the variations in C-band comparing it to L-band?
Yeah, so I mean here the difference in wavelength is the big thing here, because it means that we have different radar penetration depth. So in the C-band images, we are primarily seeing backscatter signatures that relates to the surface roughness of the sea ice. And in the winter, we say that the snow is generally a dry snow. The radar penetrates through, so we're seeing this sort of snow-ice interface. The L-band with this longer penetration depth, there we're seeing interaction within or between the radar and the sea ice itself. So we're looking at the porosity and these things in the sea ice. So that's one of the two big changes. So the C-band is the snow-ice interface, and the L-band is within the ice itself. we also have different levels of deformation at the surface of the sea ice, where the seabed will be more sensitive to the small scale roughness, whereas the L-band will be sensitive to slightly larger scale roughness, where the difference between the 5 and the 26 centimeters is what's coming into play here.
Okay, question number 9, and this one asks, does the combination of L and C band support flood detection as well? I'll just start out by adding that this is probably going to be addressed in the third session of this webinar series. So that'll be the presentation on using SAR for detecting and monitoring floods on Wednesday, November 1st by Dr. Franz Meyer. But if you'd like to add anything else to this, Dr.
No,
Johansson?
I'm very confident that Franz will be able to answer this very well, much better than I can.
Okay. All right, then let's move on to question number 10. Do we need to calibrate sigma naught before doing the alignment?
Right, so here, well, the images I've been showing has been aligned, and that is if you want to actually compare the different data, yeah, you want to have them calibrated and, in as good state as possible. So yeah, ideally they should definitely be aligned or calibrated before we align them. I also point towards some quite recent work here between where they aligned L and C-band data for drifting sea ice. So you're really taking this to the sort of next level where we're trying to align something that can move with a number of kilometers per hour if we're unlucky.
Okay, question number 11 says, I only have a PDF in my image file. Did I download it incorrectly?
Oh, I guess we need to look at that, but it shouldn't, is all I can say for now, but maybe we can look at that after the lecture to see that the right data is there.
Yeah, absolutely. We'll verify that, and shortly after the end of this session, we'll verify and ensure that people have access to the right file. Question 12. Can graphs be used to monitor trends and changes in sea ice?
Oh, I'm not the right person to answer this question, I don't think.
Sure. So we can get back to that question.
Yeah.
So this, by the way, this document will be posted online within the next few days. So we'll clean it up and we will be addressing all questions. So question number 13, can you please elaborate more on the multi-frequency approach?
Right, so that is something that is quite new in the sense that now we have a lot of available data. The addition of Sentinel-1 being freely available since 2015 means that we have a lot of C-band data available, and more L-band data is becoming available now as we speak. YACS is making most of the ALOS-2 SCANSO data freely available. And there has also been a number of collaborative efforts between the different space agencies in providing data that is acquired over the same area at roughly the same time, so that we can have images that are in both C and L band. And obviously for the Antarctic NISAR will be a game changer in having more L band data there as well. So what we know is with the different penetration depths, we retrieve different information from the sea ice. And with that, we can use the differences in the responses in the L and the C band to get more certain of the sea ice types that we are looking at. So we know that the L band is more sensitive to the younger ice types. And we can see the changes in some of the younger ice types occurring earlier in the C band than it does in L band. And this can give us some indication on the ice growth rate. We have known for quite a long time now that the L band is much more sensitive to the roughness and deformation, so the ridges and these things that are challenging for us for the shipping. And then by combining the the L and the C band, we can then have more information about the deformation areas. Both the L and the C band have different sensitivities to the onset of melting. So the L band is a bit slower in the take-up when the snow and the ice starts melting. So we then have we keep sort of the winter conditions in the L band for a little bit longer. But once we get to the advanced melt season, where we have the melt ponds and we have basically a completely saturated snowpack, the separation between the different ice types is much more obvious in the C-band data. So by combining them, we get a much more confident and reliable sea ice mapping year-round.
Okay, question number 14. This participant asks if this is SAR interferometry or SAR polarimetry.
Oh, relating to what in the lecture? I did not cover interferometry, so I guess that should answer. There is also some work done on SAR interferometry of sea ice to detect ridges, which has been quite successful, but I did not take the time to include that in today's lecture. So when I've been talking about, I have been talking about the polarimetry rather than the interferometry.
Okay, great. Question number 15. Is it possible to use these methods to monitor rivers?
Yeah, if you're talking about sea ice on rivers, yes, it is. There has been quite some great work done by Torsten Gelsetzer recently about looking at river ice. It's freshwater ice, so it's a little bit different. We don't have the same pores and the same SAR signatures related because we're simply missing that salinity. But yeah, it's definitely possible.
Okay, the next question. It's a great question, actually. I see that HV is a great polarization for detecting sea ice. Can you explain why that is? I've seen a lot of publications using VV for detecting oil slicks on the ocean, which I imagine would be similar to grease ice.
Yeah.
Is there a difference between these applications for HV versus VV, or is there an opportunity to further leverage VV for sea ice detection?
Oh, so the HV is a great polarization for sea ice. That is correct. Obviously, the cross polarization channels, we have some issues if we have very low backscatter areas, such as for oil slicks and also for grease ice. So grease ice is one of those oil spill lookalikes where we cannot actually easily separate grease ice and oil. We can often not use the HV simply because of the signal to noise ratio. It's too low. I believe there will be quite a lot of VV data using NISAR over the Antarctic sea ice areas. By tradition, when we do this operational monitoring, we want to have a consistency in the data acquisition. So boring acquisitions, as I heard him mention, where we don't change things from time to time. So a decision was made quite a while back that we often do the HH and HV, and this means that we know quite well what the SAR signatures should roughly be for these frequency bands, or sorry, for these channels.
Okay, question number 17. Is the thermal noise removal in SMAP a simple subtraction of the noise equivalent sigma 0, or does it use the Nansen center algorithm?
It does not use the Nansen center algorithm. It's a simple subtraction of the noise equivalent sigma 0 with some adjustments, but it is not the Nansen center algorithm. That is that is easy to implement, and you can go to the GitHub laboratory and you can get the Nansen center algorithm, but that is not the one that is inbuilt in SNAP.
Okay, and along the lines of SNAP, then the next question, number 18, how do you decide which SNAP pre-processing steps are necessary to undertake when looking at sea ice?
Well, I guess here, building on the shoulders of giants, as the saying goes, this has been developed over many years by many great scientists. So that's we have, I would say, established some steps that are necessary to get data into the good quality. There are some people who use a terrain correction as well. Not everyone does. So that's a little bit of a debatable, but yeah, what I tried to include in this exercise here were the sort of the standard ones that most of us make use of.
Question 19, going back to the use of different frequencies, can you speak to the use of KU band, if any, in your research and airborne sensor utilization versus satellite data?
So the KU bands is more related to the snow pack. So it is definitely useful. And it's used towards altimetry and these other applications, but it's not yet used so much for SAR applications. So, but I urge you to look. There is a lot of great science being put out now about the utilization of KU band. We can provide some links after the chat.
Yeah, and I'd like to add to that. Back when I did my PhD, part of it was using KU band, actually KU band from QuickScat, to look at the onset of snowmelt. So
Yeah,
the change in dielectric and snow will cause a large change in the backscatter.
yeah.
Question, and there are many references, and we can include those here. Question number 20. How do multi-frequency approaches work given that sea ice moves between images? Can a unified time series of multi-frequency images be created using bandpass adjustments similar to the harmonized Landsat Sentinel dataset?
Oh, I'm not so familiar with the harmonized Landsat Sentinel dataset to answer that side of it. But yeah, no, this is one of the large challenges we have is that the ice moves. So we have to adjust the images. We use one as the master file, and then we have to adjust the other one as if it was taken at the same time. I pointed towards work by Denis Demchev earlier, who has done some work in now how to align the data set. There's also been quite some work done in Canada on this, so we provide some links to it. But certainly the movement of the ice is a big problem and something that we need to address at all times. That's also one of the reasons why a project called the LC project that is a collaboration between ESA and JAXA, where they try and acquire data on the same days over the same locations. It still provides a time separation because the L-band images are taken later in the day than the C-band images. So this is ALOS-2 and Sentinel-1 I'm talking about. But at least having them with a few hours time separation rather than days makes our lives a lot easier.
Okay, question number 21. Is there a way to track the Python code used for analysis from the SNAP desktop so that we could use these same methods inside cloud computing formats? And furthermore, allowing us to train models based off of recent classifications we built in SNAP.
Oh, I do not know the answer to this question. SNAP is generally a little bit of a black box on this. I'm not sure it's possible to track the Python code here.
We can look into that and
Yeah.
and add further information here to this answer. Question 22. Is updated satellite imagery accessible free of charge? And if yes, can we have a link?
Yeah, I mean, when it comes to Sentinel-1, yeah, it's uploaded within a few hours at the most. So yeah, we should be able to provide links to ESA, and I guess, well, NISAR is not up yet, but we will provide links to those that are freely available right now.
Yeah, and as a heads up, the presentation on Friday by Dr. Franz Meyer, he'll be talking about floods, using SAR to detect and monitor floods. And he'll also be showing some of the tools on the Alaska Satellite Facility and different SAR data sets that can be accessed through the Alaska Satellite Facility. Okay, so let's move on to question number 23. How can SAR images be used for permafrost studies and monitoring? Which frequency is optimum for it? And what polarization bands are useful? What time period does one need to consider? And can the current commercial satellites like ISI, Capella SAR be useful for it? So this is a multi-part question.
Yes, and covers a few other. We will provide some links to works by others who does use SAR images for permafrost monitoring after the Q&A here. L-band frequency is generally one of the preferred frequencies. And I believe that they are using the VV band, but again, I'm gonna look this up. We obviously, when it comes to the permafrost, the time period of most importance is when the permafrost starts melting. And then also having a reference in winter when it's not melting. The current commercial satellites are quite useful for these things. They also cover, some of them have a very high repetition frequency, and others, they provide data at the same time as we have optical sensors as well. So the commercial satellites are certainly providing quite a lot of useful data for these applications.
Okay, question number 24. Sorry, I think, so that's been repeated. Question 25. What have you found are the largest challenges to using SAR data? It seems like there is a lot to consider when using SAR.
Yeah, certainly there is a lot to consider. So I'm just now going to talk about sea ice. So the biggest challenges we have there is the separation of multi-year ice from young ice, and also separating of open water from all the different ice types. This is a challenge we've been battling for many years already, simply because the high backscatter that we get from some of the young ice types, it looks very similar to those of the multi-year ice. So we run the risk of telling ships that we have an area where we have a lot of deformation, when in fact we only have 5 centimeters of sea ice. So this is one of the largest challenges for the ice classification when using SAR images. But yeah, I mean, I was bringing up all the challenges that we need to consider. And for a lot of these challenges, if we know what they are as humans, and also we can train our algorithms to account for them. So like if we see something that we are sort of wondering, is this actually true? If we know what kind of challenges the SAR images are having, we can then make a decision that, okay, yeah, this was a challenging image that we were looking at, but I actually trust my result because of the knowledge that we have of the SAR image itself. If that makes sense.
Yeah, great. Thank you. Before we move on to the next question, there was I want to address one of the previous questions about SNAP, the tracking Python code from the SNAP desktop, and a participant typed that there is a Python API for accessing SNAP tools, and the best way is to install SNAP and configure the Python accessibility during the install process. So we'll add this information to that answer. All right, so let's move on then to the next question, which is a very interesting one. Number 26. Do changes in salinity values in the Arctic Ocean from melting of freshwater glaciers on Greenland affect the spectral, I guess, spectral and backscatter signatures of sea ice?
Well, yeah, so if you have some of these areas where you simply have a freshwater layer, you are in fact then freezing freshwater rather than freezing salt water. So yeah, then you have the similar situation as when you have the rivers that we talked in one earlier question, is that you have a freshwater ice layer.
Okay, question 27. Question 27 says, I'm interested in knowing ways to solve the incidence angle effect, and it's usually not clear in the literature and in the community. Usually it refers to SAR images, and some people even believe the calibration step in SNAP deals with it. Which procedures do you recommend to eliminate the incidence angle, and do we have to apply them to different types of images, such as SAR and strip map? Especially for strip map in a single SAR image, maybe we don't apply the incidence angle correction. However, do we need to keep in mind, do we need to have in mind, for example, normalizing to a specific angle? Okay, so the bottom line here is, do we need to correct for incidence angle effect depending on the type of image?
I would argue that we do need to account for it. Some people will then calibrate, instead of using sigma naught, using beta or gamma as a simple way of adjusting for the incidence angle effect. The calibration step in SNAP does not deal with the incidence angle effect. So I think I pointed towards some work by Malik Mahmoud over sea ice, where he then defined an incidence angle effect, or what he is using then to adjust the entire scene. There's also some work by Park in the cryosphere. We provide the links soon, where they also used a single or one value across the scene. That's the simplest way of doing it. We say, okay, we know something about the incidence angle effect, and we're going to apply a one slope fixing it all approach. Yeah, we definitely need to apply them to SAR images. I'm hoping I've proven to you that the effect is there and we need to deal with it one way or the other. The strip map images, we have less of an effect simply because we have less of an incidence angle degree range in these images. But you need to account for, especially if you would compare, for example, two strip map images over the same area, but has different incidence angles. Like, how do you compare a value of minus 25 in one image, and you say the next image is minus 35 decibels? Is that because of different incidence angle, or is that an actual effect? So especially if we're looking at time series, we really need to account for it so that we are comparing apples and apples.
Okay, question number 28. You mentioned an advantage of combining SAR scenes with different bands. Are there any plans to design a satellite with multiple or different SAR bands? I think that's every radar remote sensing scientist's dream, right?
Yes. And NISAR will have L and S band, of course. So there we have two SAR bands that will be acquired nearly simultaneously. But yeah, there is. So yeah.
Yes, and looking forward to NISAR, which it will be launched the beginning of 2024. So that's going to be a great data set.
Yes.
Question 29. SAR is said to be transparent to dry snow. However, there are studies from the sea ice and glaciology community on this. How useful is the use of SAR for snow thickness? And I will appreciate some references if possible.
So the KU band that was raised as an earlier question, there we can start talking about the snow thickness. It's not necessarily that easy with the XC and L band images that we have primarily talked about today. But yeah, we will provide some references, and yeah, we are always talking about saying that the SAR is transparent to dry snow, but I think more and more evidence is showing that that is not entirely true. We're also starting to have more of rain on snow events in the winter in the Arctic. And that means that the snow is not dry anymore. We cannot say that just because we're in the freezing season, we're having a dry snowpack. And also when we get to the marginal ice zone, we have a lot of waves that splash up on the ice itself. So there the snow also isn't dry. But we'll certainly provide some references to this.
Okay, question 30. Is there a possibility to use SAR to detect surface water pollution?
Well, I guess we'll refer to the oil spill lecture from last year. And I'm sure there's some other earlier NASA ARSET lectures as well on surface water pollution.
Yes, absolutely. Those are using optical data, and we can include those links here. Question 31. Does the ionosphere or rainfall play a role in post-retrieval in SAR images? Is that something taken into account in the quality control band? And if it is it a reliable indicator of the quality of the pixel?
Yeah, certainly the ionosphere is playing a role in the quality of the SAR images, particularly when we get to L band. There, for most of I think NASA and ESA and JAXA and the other satellite service data providers, they do quality control checks on this, but there is generally a little bit of ionospheric effects remaining at times. It's less of a problem in the X and the C band.
Wonderful. So that marks the end of our questions. Unless there's anything else coming in right now. No, that was it. So, and it marks the end of this first session. I would like to thank the ARSET team for all their efforts in making this possible. Selwyn Hudson-Odoi, Brock Blevins, Natasha Johnson-Griffin, Sarah Kutschall, Sean McCartney, Jonathan O'Brien. And I would like to thank all participants and remind them that the recording for today's session will be online in the next couple of hours. I believe the presentation is already online. And finally, remind you that the next session, which is on detecting subsidence due to groundwater extraction using interferometric synthetic aperture radar, will be next Tuesday, October 31st. And it will be a lecture by Dr. Eric Fueling from JPL at the same time. I would like to especially thank our guest lecturer today, Dr. Malin Johansson, for a really great presentation and again for being so generous with her time and sharing her knowledge and experience. So before I close, Dr. Johansson, would you like to say any final words?
No, I'm just happy to receive all of these very interesting questions as well. It's great to have such knowledgeable audience.
Absolutely. So with that, then we will see or hear each other next Tuesday. Wishing everyone a great day and keep tuned for the Q&A transcript and the recording. Thank you, everyone. Bye-bye.